All right, so what I want to look at in this lecture is the idea that of what friction is first, and then go over some of the worksheets. So friction, we've already started talking about. Friction is a force that opposes motion. We can also say that friction always points parallel. Let me write this as well. So always points parallel to the surface. This gets at the idea that surfaces aren't completely smooth. You know, even when we have a really smooth surface, if we look at the microscopic level, we see that it's quite rough. And these interactions between two surfaces produce friction, produce resistance. And so we have a force that opposes motion caused by the microscopic interactions of rough surfaces. And sometimes it's not too microscopic, right? Obviously, some surfaces are clearly quite rough, and so friction isn't surprising at all. So really, that's what we're dealing with here. We like to designate force friction like this. And that's fine. You could also maybe just write FF like that. Something about friction is if we think about, say for instance, you have a couch. I don't know if I can draw a couch very well. It's not bad. Okay, so something like that. You have a couch, and the couch is sitting on the floor, of course, and you decide you're going to push the couch. We know that if we give the couch a force, we'll say to the right here, force push, that we expect there to be a counteracting force friction. Now, what we know, but from experience, right, that we could walk up to the couch and push lightly, and force friction would balance, right? So what I'm saying is, you might push on the couch. I'm not going to redraw the entire couch. If I just draw this dot here, you might push lightly on the couch like this, and the couch doesn't budge. Sorry, here's your force push. And we know that friction matches the force. We also know maybe you push a little harder. Say, for instance, here. Whoops, keep drawing the friction force first. Say, for instance, right here. And friction matches that. So here we see three examples where you try and push this couch, it doesn't move, and force friction matches it. We call this kind of force friction static, meaning the object is not moving, it's static. So when you think static, you can think stationary, right? Not moving. So what I'm saying here, when we have friction that is static, we'll call it force friction, comma, S. And this just means force friction static. And what we see is that this matches up. What's up?
Sorry.
Oh, you're good. I'm okay. So we also know that that there's if we push this couch, there's a point where the couch just begins to move. And this is where the force friction static hits a maximum. Maybe it's in, if we go back up here, maybe it's in this top drawing right here. That this is where force friction static, right, is at a maximum. That this is force friction static right here, that this is force friction static right here. But in this drawing right here with the couch actually drawn on here, this is where the force friction can no longer be as large as the push, and the couch just begins to move. So I'm going to write that down. I'll just make a little note right here. Couch just begins to move. So it's still an equilibrium situation right there when it just begins to move. But we will see that in problems going forward. The next thing we can say here is that if we start moving the couch, right, we know from experience, from moving a heavy object, right, that it becomes easier. So as the couch is moving, so if I redraw the couch down here, so here's the couch, obviously not as good as last time. I don't know, maybe something like this. Okay. All right, anyways, I'll put a dot on it. And we are pushing the couch with a force that is actually going to be smaller than this one right here, because now it's easier to move while it's moving. So right here, the couch is moving. We'll give it a velocity to the right. It's some velocity v, right? We don't draw velocity on the free body diagram. I'm just going to put it up there. And maybe it's a constant velocity, so I can write v constant. So the couch isn't speeding up, but it is moving. And what I'm saying here is that this force of the push is going to be less than what it took to get it moving. So I'm going to make it a little smaller than that vector, or try to. Maybe about right there. And we'll say this is the force push. And we have, instead, with this direction, we still have friction, right? The surfaces are still interacting. They're still not perfectly smooth surfaces. So there's definitely still friction. But we can call this force friction from movement, right? So we like to call it force friction with a K next to it for kinetic. So force friction kinetic. So I'm going to go ahead and write that down right here. I can put a comma there. That's fine. And the word kinetic means movement. So you can think of it, you've seen this before, maybe you've heard of people studying kinesiology. maybe if they're going into movement studies, or they're going to, yeah, that was a program I was in when I was in college, was kinesiology. You could also, you also see it maybe in words like cinema. Cinema for a movie theater, right? You think about this. This is moving pictures on the screen. So cinema comes from the word kinetic, and so you can see similarities there. But kinetic means moving. So, anyways, let me go ahead and pause. All right, so we keep getting interrupted here. I do, but that's okay. So coming back to static friction and kinetic, we can say, and we can compare force friction static when it's at its maximum, right? Not because we know it can change on us, right? We saw that a second ago. We saw that the purple force was larger and when it was, or we saw that force friction static matched the force of the push, right? So we had 3 different push forces, and force friction static changed relative to that until it hit its maximum. So we can compare force friction static max to force friction kinetic. And we know that it's always easier to move the couch when it's moving, so we can say that force friction static max will always be larger than force friction kinetic. Now, obviously, that wouldn't be true for every force friction static max, right? Because if you just push barely on the couch, then friction doesn't have to push back that hard, right? So then friction wouldn't be that large in that case. So we can just say this for the static max. All right. And that is the one we are mainly going to deal with in class, but we'll see instances where we will deal with force friction static and it's not at a maximum. So that will occur. Let me add another sheet of paper here. Okay. All right, good. Let's quantify friction just in general, not static, not kinetic. Let's just quantify it. So what we have is a formula here that says force friction is equal to mu times Fn. So Fn is force normal. And this is the reactionary force from the surface directed perpendicular to the surface, right? So if I had an object sitting here, we know that force normal points normal to the surface, 90 degrees to the surface, so points like that. And it's reactionary. So it requires a surface to even exist. And it doesn't always equal force gravity. In this case, it would, right? Because force gravity points like this, and it would be equal. It's not a Newton's third law pair, though, because both forces exist on the same object. So that's tricky. They're equal and opposite, but not a third law pair. Okay, so there's force normal. And this can either be, this is obviously force friction, but it can either be kinetic or static. And we'll talk about that in a second. This is mu, the Greek letter mu. And what it stands for is the coefficient, which is kind of a fancy word for number, the coefficient of friction. And what the coefficient of friction is, it's a number that relates force friction to force normal, right? It's a number that relates the two, and we call this mu. Because, so let me write that down. I'm going to write out the word friction. It's really like a ratio of forced friction to force normal, right? I'm not sure if I can technically use the word ratio there, but let's look at what I'm saying there. So with the coefficient of friction, we can rewrite the formula we had above, right? The formula above was force friction equals mu Fn. We can rearrange that, though, to be mu, and solve for mu, is equal to force friction over force normal. And so here is an equation for the coefficient of friction. And we can kind of see the ratio or the comparison or the relationship between force friction and force normal. And this is the idea behind mu. Now, mu is a number that, well, it's a couple things. I'm thinking of how much I want to tell you about this because one of my labs goes over this, but let me go ahead and just tell you, it's fine. Mu doesn't depend on mass. It's a number that comes from the interactions between the two surfaces. And by interactions, I mean the frictional interactions. So what I'm saying here is that we determine mu experimentally. And there is a different mu based on the two surfaces. And furthermore, we can say that a greater mu equals more friction, or means more friction. And a smaller mu, right, because it's just a coefficient, right? It's a number, equals less friction. Let's see here, one more page. Close this. So typical mu values, I would say between 0 and 1. But for some surfaces that have a lot of friction, maybe something like Velcro, something that is just a ton of friction, mu can be greater than 1. So don't think that it can't. It definitely can. So let's write that down. But mu can be greater than 1. So a lot of times in physics problems, we will get mu values of like 0.75 or 0.5 or 0.3 or 0.2. So a lot of times these mu values are between 0 and 1, typically, in our physics problems, but it can be, mu can be greater than 1. All right. Okay, what else can we say here? We can even compare mu static and mu kinetic. We can say that mu static maximum is always greater than mu kinetic. So one more thing we can say is that mu static will change. So sure, mu static can have a maximum, but mu static itself will change based on the friction static required. I'll probably go more into that. Well, what I'm trying to say, let me see if I can say it right now. What we can do is we can write, obviously, force friction static is equal to mu static times Fn. So if we think about the couch always has the same normal force when you try and push the couch. And the reason why it would always be the same is because we said for the couch, it was similar to the crate that was just sitting there, right? Meaning that it was always equal to force gravity. So if I go back up and look at that crate or that box that I drew, we saw the normal force was always force gravity, right? Because the couch is just sitting there. So we would expect something like this to happen. It's not on an incline. There's nothing that should change your normal force, although normal force does not always have to be equal to force gravity, but we saw that that's the case. So what I'm getting at here is we had different force friction statics, right? This was changing. So how could that be possible, right? If force normal is always the same, then mu static would have had to be changing. And so this is why that you can have different mu statics, but you can also have a mu static max, where that is the point where mu static can't get any larger. But with moving friction, mu k isn't going to change unless you change surfaces. So while mu static was changing, it only got as large as the max, right? And you can write here up to the max, right? Because obviously it can't go past the maximum. That's the most friction static that you're going to have. Okay. Good. Hopefully this is making sense. Boy, I keep adding more pages. Well, all right. You can see sometimes why these lectures go so long. So we can also write, just like we wrote this, right? Force friction static equals mu static times force normal. We can also write force friction kinetic is equal to mu kinetic times force normal. All right. So, good. I think we are getting, or we could also write it this way, right? Of course. But I think we're getting close to the point where I think maybe just some sample problems would be good. And let's look down here and see what else we have. So I rewrote this formula this way. We wrote it this way. I guess another way to write it, which we didn't write it yet, would be the last way would be like this, right? Mu static. Should we write it as max? I'm not going to write it as max right now. I'm just going to write mu static is equal to force friction static over force normal. So 4 ways to write that formula, right? But notice that the statics always go together, that the kinetics always go together. We don't mix the two, right? Either you have static friction because the couch isn't moving or just began to move, or you have kinetic friction because the couch is moving. Okay, let's go down and look at some of the practice problems we're going to do. So here you can see not too tough here. This is just going to be using your formulas to solve. Remember, you might have to solve for force normal. I don't think you do here, but in a lot of times, if the object is just sitting there, force normal will equal force gravity, which is force gravity is mg. Let's look at, let's maybe jot that down just so you don't forget, right? These are some other formulas that you might need for these worksheets. Fg equals mg, right? This is our weight formula. And then a lot of times, if the object is just sitting here like this, then Fg will equal Fn, right? And in that case, we have sum of the forces in the y direction is equal to may. It's not accelerating, so therefore ay is 0. We can plug in our forces. Force normal points up, force gravity points down. This is 0 now, and we can see Fn is equal to Fg in a lot of cases. Now, this isn't always going to be true, but sometimes when an object is just sitting there, then obviously it is on a flat surface. If it's sitting there on an incline, then it's not true. So I just want to point these out because in some of these worksheets, you might have to solve for force normal. And then they might expect you to come to this conclusion that force normal is just mg because Fg equals Fn. And yeah, all right. So coming back down here, something I want to point out, and there's a little reading here if you want to do it. They have a table of coefficients of friction of different material when these materials move against each other, right? So steel on steel, aluminum on steel, rubber on dry concrete, and so on. Over here, ice on ice, Teflon on Teflon. And you can see we have mu s and mu k. We can also see here that mu s is always, and here they're going to mean maximum. I don't think they go out and say that, but this is going to be our maximum mu s. And you can also see that mu s max, right, is greater always than mu k, right? And if you look at all these values, let's just compare two really quick. 0.15 for mu static max for metal on metal, and 0.06 for mu k. And notice the values tend to be between 0 and 1. We have 1 value rubber on dry concrete, which is a value of 1. It can be greater than 1. None of these are here. But, there was one that looks like the hole punch kind of ruined. I don't know what that was. I'll have to, if you want to know, let me know, and I'll tell you. So you have some sample practice down here in practice D. And I know in some of these, you have to reference that table because here you have like aluminum sculpture moving across a horizontal steel platform. So you would have aluminum moving against steel, and that should be up in our table here, aluminum on steel, and you can see it right here. It looks like I wrote on the sheet here. And if it was moving, and I think it was, right? They say moving, a 145 kilogram aluminum sculpture. So if you're moving it, they tell us, we tell us to find force static max and force kinetic. Those would be friction. Notice they didn't put the F in there, right? But those are both frictional forces. I like to write a little more, I guess, than they do, and that's fine when I describe the forces. But you can see that you're going to have to use mu static to get force friction static max, and you're going to have to use mu kinetic to get force friction kinetic. All right, hopefully that's making sense and that's clear. If not, do the reading, that small reading that I gave you right there. And then obviously you can always rewatch the lecture and maybe it'll make more sense the second time around. But there you have it. This is kind of, this is what forced friction is about. And if we can, maybe we'll get in the lab and do a lab on this. And if we're virtual, we can always try and make a lab work as well. So anyways, all right, have a good day.